All right, so we're starting our quantum mechanics unit here. Um, this is the first unit where the difficulty level starts to rise. Not so much in the skills are difficult, but that it's very abstract. This gets a little wacky. And so as you're watching these videos for this entire unit, especially when I get to the quantum mechanical model, it may take you watching it more than once to get a firm grasp on it. When I teach this to my students, I tell them it takes 2 to 3 days of 1 hour lectures of like, I'm going to go through it faster than that, and you should be able to follow along because you just go faster in a video than you can with kids. But it takes time to understand what's going on. So give yourself some patience in this unit. It's going to be needed. So there's just some wacky things that we just got to deal with. So, all right, so we're starting off with wave physics, where physics and chemistry meet, what I got written here. And part of the wave physics it applies to where we're going. Also, once again, it's included in a lot of state standards of things you need to know. So we start off with the electromagnetic spectrum. That visible light is part of what we call the electromagnetic spectrum. And this spectrum includes a wide variety of waves: TV, radio, cell phones, UV, X-rays, gamma rays. All those are included within the range of the electromagnetic spectrum. So all of these are waves, including visible light. And so we need to discuss the parts of a wave. So waves have key parts that we need to be able to identify and key properties you need to understand. So A, the top there, is called the crest. So this is the crest. B is the trough. C, which is the height from the midline to the top, or from the midline to the trough. So midline to the crest, or midline to the trough, is called the amplitude. And then the wavelength is from one point to when that point repeats. So from here to here, or from here we're at the midline going up to here we're at the midline going up. Okay, that would be a full wavelength, the length of the wave. Wavelength is given the symbol lambda. Okay, it's Greek. It's just the Greek letter L, but that is the symbol used for wavelength. Frequency is given either an italic F or the Greek letter nu. Looks like a V. It's not a V, it's actually the Greek letter nu. I think people got tired of the confusion with nu. And so most books and things you see today will use that italic F, and that's what I'll be using. I learned it with the nu. That's how I grew up learning it, but I now use the italic F just to avoid confusion. So wavelength and frequency are related to each other by what is called the wave speed. And it's very simple, that the wave speed, or V, velocity, is equal to the wavelength times the frequency, lambda times F. So waves of a particular type will move at the same speed under the same conditions, meaning the speed of sound is the same wherever you are. No matter who's talking, the speed of sound is the same. The speed of sound is different underwater. The speed of sound is different through a railroad track. That's why people put their ear down to the track, because they can hear it sooner, because the speed of sound is actually significantly faster through the railroad track than it is through the air. Same thing with the speed of light. Speed of light in a vacuum is a constant, and it is 3 times 10 to the 8th meters per second, or 186,000 miles per second, which is ridiculously fast. I mean, so it can do, think about it, how many round trips across the country in a second is 186,000 miles. That's how fast light moves, as opposed to sound that moves 700 and something miles an hour. That's why we see lightning before we hear thunder, because light moves a lot faster. And so we use the C, which is the speed of light in a vacuum, and we say it's equal to wavelength times the frequency. So we can then use this formula, C equals wavelength times frequency, and we use it to calculate or convert from frequency to wavelength and back and forth for any electromagnetic wave. So for example, What is the wavelength of a radio wave at 98.7 FM? So the frequency of that radio station is 98.7 megahertz, or 98.7 million hertz. So writing that in scientific notation is 9.87 times 10 to the 7th hertz. Okay. So then we can simply plug that into the equation. So we take our equation, and I'm a big fan of always writing the equation first without any numbers put in. And then you plug in your numbers. So C is 3 times 10 to the 8th meters per second. Frequency is 9.87 times 10 to the 7th hertz. Divide both sides by 9.87 in order to solve for lambda. You get lambda is 3.04 meters. Okay, so it's a relatively simple calculation, and that is the basics of wave physics.